So we're going to let these, I assume all doctors, introduce themselves because we saw a lot of names of doctors. So we don't know how to introduce you. We are happy to have you. You're talking about things that to me sound very, I would say, highly technical, jump-oriented programming exploits. So for those of you who are interested in some advanced exploits, let's go ahead and give you to the virtual floor for now. And hopefully the third presenter will show up shortly.
Hey, who do we need to make presenter?
I'm here. I'm the one with the problem, Josh.
Excellent.
Oh, Josh, I have the no webcam issue.
He's just our ghost.
I'm just a voice attached.
Who should be presenter?
I would like to start.
All right.
Yeah, we're here. Pleasure to meet all of you, and thank you for being here, part of the conference.
Yeah. Great to be
here. Thank you. Okay, so show my screen. Hopefully, yes, you see the first slide.
We see a cat with a rocket.
Yes, you
see a lot of those.
You're going to see a lot of those. Yes, it's part of the experience.
Relevant to your interests.
All right, we're going to go camera off. We'll be here if you need us. If you do need to switch presenter, just let us know and give us a couple seconds so we can get to the right screen and switch for you. Otherwise, Josh, you might be able to right-click and go to webinar and make someone else presenter. I'm not exactly sure, but if that doesn't work, just say who you want to be presenter and we'll make it happen.
All right. Well, thank you for that. So I wanted to say welcome to our talk, Jump-Oriented Programming Exploits with the JOP Rocket. I apologize, I'm having issues with my camera, but I'm only providing a brief introduction, so it shouldn't be too big of a deal. I wanted to first thank Wild West Hackin Fest, Black Hills Info, John Strand, everybody that's a part of the team there for making this happen. While we wish we were there in person, we are definitely excited and appreciate the opportunity to do this virtually. So real quick, presenters today. The primary presenter will be Dr. Bramwell Brizendine. He is Assistant Professor of Computer and Cyber Sciences at Dakota State University, Director of the Verona Lab, where he focuses on vulnerability and exploitation research, and most importantly, the creator of the JOP Rocket, which you'll learn more about here in just a few moments. I am the voice without a face, Josh Stroschein. I'm also an Assistant Professor at Dakota State, where I run the Madrid Lab, focused on malware analysis and RE. I also do some work for OISF, Suricata, Chromium HP, and some stuff with the National Guard. Also joining us today is Austin Babcock. He is a graduate student at Dakota State University, where he is getting his master's in computer science with a cyber ops specialization. And you'll be hearing a lot more from Austin in just a few minutes as well. So what are we going to cover today? Well, besides introducing you to a large number of CAP backgrounds, we are going to talk a little bit about memory corruption and start by discussing a real brief primer refresher on return-oriented programming. The JOP technique, or using JOP for exploitation, requires a vulnerable program. We're going to be focusing on memory corruption, and so just want to set the stage there a bit. I will get into just a real basic introduction to JOP before we get into the finer details. Then Dr. Brizendine and Austin will get you strapped into the JOP Rocket, introduce some finer points of JOP-based exploitation, show you the magic of JOP with some demonstrations, and then also introduce some of the pre-built JOP chain generation that is now part of the capability. We wanted to first start off by saying that we did not create the JOP technique. Literature does provide us with some examples going back about a decade. There are some references there if you're interested in doing a little bit of research. There were some serious limitations, and so some of the motivation behind this work was that there really was no tool to facilitate JOP gadget discovery. There was very little documentation, or really no documentation, on doing JOP in a Windows environment. And then we will be focusing on Windows environments for the remainder of this talk. There are some claims that JOP has never been used in the wild. That's not exactly true. But again, the academic literature was very vague on the practicalities of usage, and certainly not in the Windows environment. Fortunately, we had the honor of introducing this work at DEF CON 27, so just a little over a year ago now. But since that time, there are many changes, many advances that you will learn about in more detail today. So let's start low level. As I said, you need a vulnerable program that has something that is exploitable. This means that we'll be dealing or focusing on memory corruption. So if we take a sample program for our scenario here, let's say it's written in C or C++, those programs are then run through a compiler. The compiler generates the machine code, the actual literal ones and zeros that get loaded into memory and executed by the CPU. Now, those generally get put into native code binary file formats, PE files, portable executable for Windows, ELF, and Mach-O for other operating systems. Those files get interpreted, parsed by the operating system, loaded into memory, and then that's where execution by the CPU begins. So our programs, while they largely they maintain the same file format from disk to moving in memory, there are some changes that we can get into. But the focus here is that we'll be looking at the technique as that program is being executed in memory, either the program itself or maybe a library. A very brief history on ROP. If you look at the literature, a lot of the research, the history points to ret to libc, return to libc as a precursor to ROP, return-oriented programming, primarily a Linux thing, and there's one of the leading authors if you want to dig into that background a little bit more. Return-oriented programming, then, what it does is it's, as you see this back and forth between ability to exploit programs and mitigations that were put into place, DEP, data execution prevention, was one of the primaries. So we have these basic buffer overflows where we corrupt the stack with pivot EIP to execute code on the stack. Well, with DEP, DEP makes the stack non-executable. So how do we now exploit the program? This is where ROP comes in, and then instead of relying on execution on the stack, we're borrowing chunks of executable code from memory. So we use the stack still, and this is an important point, we use the stack still for control flow, but the flow then goes to different regions of executable code. Those little, we'll have gadgets and chains. So our gadgets end in a ret, so a few instructions and then a ret goes back to the stack in order to go to the next gadget. So gadgets are a series of instructions ending with a ret. Again, we control the flow with the stack, and a sequence of these gadgets then becomes a ROP chain, which allows you as the exploiter to do something functional. A lot of tools out there. Some of the more prevalent or popular would be Mona by Peter Van Eckhout and ROP Gadget by Jonathan. You can find those tools. Likely, if you're into exploitation, you've already come across them and maybe used those yourselves. So, as I said, there is some pretty key differences here between JOP and ROP. One of the major differences then with JOP is that we're using jump and calls to order the control flow. We are not able to use the stack to control the control flow. That doesn't mean that the stack doesn't still play a role here. We can still use the stack in order to prepare for function calls, but in terms of the flow of the JOP gadgets or the JOP chains, we're just not able to use that. So what do you need to JOP? You need three things: dispatcher gadgets, dispatch table, functional gadgets. So the dispatcher gadget is what's going to allow us to control the flow both backwards and forwards into the dispatch table. The dispatch table then is what's going to hold the addresses to functional gadgets. So think of this as a container of function pointers. The functional gadgets then are going to be what probably is most closely related to our traditional ROP gadgets, and that there'll be a sequence of instructions that we will chain together in order to accomplish something functional. The difference here, though, is that these will terminate in a jump or a call and take you back to the dispatcher gadget. Of course, all of this is driving towards, much like with ROP, that we're trying to call Windows APIs. We're trying to mitigate whatever is preventing us from just executing normal shell code. So we likely want to spend the least amount of time doing our ROP, doing our JOP. So calling just what's required in order to get some executable code, and then let's just execute shell code as we normally would. So here we can join Ceiling Cat and take a look at a quick visualization. We have, as you can see, starting on the left-hand side, the dispatcher gadget that then will control flow into the dispatch table. That's where all of our functional pointers are to the gadgets themselves. So depending on what functional gadget we need, we can then execute that. Again, that's a series of instructions similar in concept to our ROP gadgets that end, though, instead of a ret, instead of using the stack for flow, control flow, we're using a jump or a call. And there we go back to the dispatcher, and this process repeats until we've accomplished something functional. All right, so that's the 60,000 foot view with a little bit of history. Now I'm going to turn it over to Austin, and he will take you into a much more detailed example. All right, Austin.
So like Josh said, I'll be going a little bit more in depth into how JOP works. And so here we have kind of the similar diagram as we did before. It's the same diagram, just we're going through step by step. So on our left here, we have our dispatcher gadget. In our middle, we have our dispatch table, and on our right, we have our functional gadgets. On our left, our dispatcher gadget is going to get us from gadget to gadget. So because we have this EDI-based dispatcher gadget, we would want to load our dispatch table's address into that EDI register. And then we're going to modify that register a little bit each time. And we're going to go look at our dispatch table. And hold on a second. We're going to go through our dispatch table and look up which gadget we want to execute to start trying to set up that function call to bypass DEP or whatever else we wanted to do. And then each functional gadget is going to end in that jump EDX operation here. Doesn't have to be EDX. In our example, EDX is what is loaded with our dispatcher gadget so that we can loop back around and increment our address to our dispatch table and look for the next functional gadget here. So yeah, we'll just keep on going through that process over and over. One thing to note is that those registers that in those jumps and your functional gadgets don't all have to be the same. So let's say you had a gadget with a jump EBX that you really wanted to use. You wouldn't necessarily have to completely redo everything. You could just load the dispatcher gadget's address into EBX and then go do that. So we'll see with JOP, we're not tied to our stack pointer at all as far as our control flow goes, and that'll be relevant in a second. If we look at ROP here, we're entirely tied to our stack as far as going from gadget to gadget. So with ROP here, our stack would kind of be analogous to our dispatch table. So we have our list of each address for each gadget on the left in our stack. So if we want to go to our first gadget, we have that address here first, and then once we do a return, we just increment our stack pointer a little bit and keep going down the line from gadget to gadget, bouncing back and forth between the stack and our gadgets. And yeah, so we're tied entirely to our stack pointer for this, and it makes it really easy to follow. And but this can be a problem too, because when we use the stack with ROP for pushing and popping values when we're setting up our function calls, we have to kind of intertwine those values that we're pushing and popping with our control flow here. So if we have our first pointer and we want to pop this 40 value in the EAX, we have to put that in between our list of pointers to each gadget. So when we return, we come down to our second gadget. We will pop another value here, but let's say we wanted to push a value. So when we push a value, and I'm actually noticing that the slide is wrong, that 80 value doesn't change when we push, but just pretend like that's where we pushed. And once we push a value, ESP is going to be sitting right on the location. Our stack pointer is going to be sitting right where we just pushed. So if we want to return and go to the next gadget, we want to do more things with our ROP gadgets. When we return, we're just going to be trying to return to that value that we just pushed. And that's going to be a problem for control flow because that's going to mess everything up. With the JOP, even though JOP is more complicated in general, using the stack can actually be easier because we're not tied to our stack pointer as far as our control flow goes here. So if we have a similar situation of gadgets here where we have a pop gadget here, and then later on we move from our dispatcher gadget and look at our dispatch table and go on to gadget 2, when we do a push operation, we don't have to, even though our stack pointer is still sitting right where we just pushed, we can still keep going to the next gadget and not worry about our control flow being messed up because we're not tied to that at all for our control flow. So in a more general sense, what is our goal with JOP? Like Josh said, it's very similar to our goal with ROP. We're using gadgets, reused code in order to perform whatever operations we want to. Usually this will be bypassing DEP by setting up a function call to execute our shellcode. And yeah, so at this point, I'm going to pass it on over to Bramwell to talk more about the JOP rocket.
So as we can see over there on the left, we have our mascot, the Rocket Cat. You've seen a lot of images of cats, and you're going to see a lot more. But the Rocket Cat is our mascot. And there we have an image from an actual medieval manuscript, and it's depicting a rocket cat, and it has a flammable device strapped onto its back, and that cat is hell-bent on delivering its malicious payload. It's going to take it to the castle and set it ablaze, except, oh no, the castle is already burning, so one of its feline companions perhaps already got there. We'll follow this thread in a second, but before we do that, let's introduce formally the JOP rocket, the jump-oriented programming, reversing open cyber knowledge expert tool. So yes, just merely by using this tool, you're an expert. I think that's something we can all take a little bit of delight in. And of course, it's dedicated to these beloved felines who gave so valiantly. And let's talk about that sacrifice and how that sacrifice inspired us. So the idea here is these rocket cats, they gave their lives literally, and by the way, not historically accurate, they gave their lives literally to get into a well-defended castle. Because if you have a castle, then, if you're trying to stop people from getting in, you're going to be very successful. But the idea was that the cat could have a flammable device. It can get in there, it can penetrate the defenses, and it can do some serious damage. The JOP rocket is similar in the respect that it allows you to bypass otherwise very secure defenses. So anti-ROP heuristics, anti-ROP defenses, guess what? Don't have to worry about those. So JOP rocket grew out of doctoral dissertation research that I conducted, supervised by Josh Stroschein and Jared DeMont. And what it is, it's a Python script with some dependencies. And really, it's the first fully featured application to allow you to discover JOP gadgets. We have a number of tools that can allow you to do the same thing with ROP, but with JOP, that was an open research problem. It empowers you to do it from scratch, and big revelation, we also provide you the ability to get pre-built JOP chains. Now, it is a static analysis tool, and I decided to make it static analysis just because it's a little bit more challenging from a programming standpoint than doing dynamic. Massive program, about 25,000 lines of Python, not necessarily the best written, but it does the job. Because it is static analysis, there are some inherent limitations as far as dealing with DLLs, but I was able to work around that, and we can still extract the DLLs and get gadgets from those. So we got you covered. Some of the features here primarily is finding, classifying every imaginable category of JOP. So if you can think of it, I've thought of it, and it's going to find it, it's going to classify it. It does it by operation, it does it by the register affected. As I mentioned, it generates pre-built JOP chains. So if you want to bypass DEP, which guess what, you probably do, it's going to help you out quite a bit with that. If you are a code reuse attack guru, then there is a lot of customization available, so you can kind of personalize the types of results you get. It makes use of a thing called opcode splitting, so we discover all the unintended gadgets. When you write something, when you write your code, there are intended instructions, and there's also a vast amount of unintended instructions that you can discover if you start execution at a certain different offset. We find it all. So let's get down into the nitty-gritty of how we actually can start to use the JOP rocket to have some success with this. So we got to first pick out the registers we're interested in. Do we want EAX, EBX, ECX? We got to specify those. And once we do that, we get G for get. We go and scan the binary and find all the gadgets. We do all the classification simultaneously. We store the results in literally hundreds of different data structures. Or if you're like me and you just want everything, all the gadgets, every register, you can do the big G or the big Z, and it'll scan everything. Now, if you want to get all the modules, then you want to specify the S, so you can decide to include the modules, and then you got to go and extract them. It's part of the limitations of static analysis, but we can still make do. And then finally, we go into the print menu where we can now generate the gadgets. So let's take a look at that. This is our print menu. You want to use R to specify the register of interest, G to specify the operation. And look at that. We got a ton of operations, and this is just the first page. But don't let that overwhelm you, because if you want everything like me, you can just simply type all and you'll get all the different operations. So let's see what happens there. Okay, we got a lot of results. It does it by the register affected, the operation, and it saves it as distinct text files. It does that because if you're dealing with a really large binary, some of these can be really big. This one here is a smaller binary, but either way, it's got you covered. And one thing we may do in the future is we may also introduce an alternative printing style, but this works really well for now. And so these are some of the results. So this is a result for adding EBX. We look at add with carry. We look at EBX. We look at other smaller forms like BH, BL. Trust me, everything connected to that, we got it covered. We look at we produce the virtual address. We get the offset, and not only for the primary Indian instruction or every instruction. And with that, we're going to let Austin take over for a second. He's going to give us an example of JOP in use.
All right, so yeah, now that we have those gadgets, and notably before we didn't have the ability necessarily to find all those gadgets, so we couldn't actually play around with JOP as easily because finding those gadgets is a lot more difficult. So let's say we wanna make an exploit with JOP and kind of explore this technique. Well, we have this sample program here. Doesn't necessarily matter what program it is. It's just vulnerable. It's something to try out our technique of JOP on. But if you want to know, it's a very simple dictionary attack program against a password. And the dictionary, if you have an entry too long, it'll trigger a buffer overflow. But from here on out, we've made an exploit from this program, and we'll be looking at some examples from that demo exploit just to see how that process of developing a JOP exploit goes. And if things seem a little complicated, well, they are. JOP's complicated, even ROP's complicated. But we're going to look at that to see how JOP can make things, or the JOP Rocket can make things simpler later. But anyway, getting into our exploit diagram, just how we're moving through our exploit here, we have our buffer overflow. We're going to take control of EIP, our instruction pointer, and then we're going to set up our registers to perform JOP. So like we saw before, we need to have 2 registers set up to make our JOP control flow work here. So we have to set that up with a gadget, and then we need a JOP chain to set up a function call, which we'll use virtual protect. And then we're going to call that function and get us executing shellcode. Looking at our payload here, we have some padding until we get to our point where we can overwrite our instruction pointer. We have our JOP chain to set up our function code. We have our shellcode, our ultimate goal here. And our shellcode is very advanced, not a reverse shell, not a calc message box. We have some more padding, and that padding is just to get the dispatch table at whatever address we want it to be at. It doesn't necessarily matter where your dispatch table is in memory or even where it is in your payload. You just need to know that address so that you can load it into a register later. Looking at our dispatcher gadget, we have this add EDI, jump dword pointer EDI gadget. So we're going to want to load our dispatch table into EDI. One thing to note is that even though we've only seen dispatcher gadgets with add so far, we could have a subtract, we could have some other operation. It doesn't matter what we're doing to a register, just as long as we can put our addresses to each gadget in our dispatch table accordingly. So here we have add 8, and each address is only 4 bytes, so we have 4 extra bytes to work with here. So we just put some padding in between each gadget. These gadget pointers are fake. That's my bad. But we have some padding in between each pointer in our dispatch table. And then once we overwrite EIP, the first thing we need to do is get that control flow set up. So we need to find a gadget to do that for us. If we want to do pure JOP, we're going to have to do this in one single gadget because we don't have 2 gadgets to work with here. If we don't get our control flow set up in one JOP gadget, how are we going to use another gadget to do that? We have no way to get to the next one. But hold on a second. One of the problems we were talking about with JOP is that there's not as many gadgets available to find in binaries as opposed to ROP. And even with the JOP Rocket finding all of them that are there, we still might not have that magic gadget, that one that we need to set everything up in one go. But it's going to be okay if we don't have that because we can work with what we have. We can use some ROP at the beginning just to get things started. It's okay to use some ROP in your exploit. We're just trying to explore this new technique, and maybe it's not new, but unexplored would be a better word for it. So we're just trying to explore this, so it's okay to use some ROP at the beginning or in the middle. But one thing you want to note is that if you're using ROP, some heuristics for ROP that might be avoided by JOP, that might become a issue to think about. Anyways, we didn't have that problem. We did find our magic gadget here. So in our magic gadget here, we have EDX and EDI becoming the values that we want for our dispatcher gadget and our dispatch table address. So with EDX storing the address of our dispatcher gadget, ideally each functional gadget should end in a jump to EDX, and then EDI should hold the address of our dispatch table. But you might notice that in our setup gadget here, we end in a call instruction, and you might be wondering what's up with that. Doing jump-oriented programming, right? Not call-oriented. Well, the call instruction is the same thing as jump. Just before the jump, we have that implicit push instruction pointer. So that's pretty easy to deal with. All we have to do is put an extra pop gadget afterwards, or otherwise account for that extra value being pushed onto the stack. You just have to be aware of it. So, for example, if we had a call at the end of our dispatcher gadget, since we're doing our dispatcher gadget every single time we're going from one to the next, that call could become really annoying. So you just have to keep in mind what call does there, but we can use it. Like we're saying, we're using Virtual Protect to bypass DEP here, data execution prevention, so that we can use our shellcode, we can run it. Kernel32 contains this Virtual Protect function, and it's a pretty straightforward function. You can look all this up on the MSDN, but this is just going to modify your memory protections at the address that you specify. So when we set up that function call, we're going to have to consider bad bytes. A common theme with ROP and JOP exploits are that when you have a string-based buffer overflow, that's how you're getting your payload in, you aren't going to be able to use certain bytes. So bytes like null bytes or carriage returns or line feeds are going to become a problem, because when it encounters that byte, it's going to think your string is over and stop reading it into the buffer. So you can't put those bytes into your payload, or your exploit's not going to work. But we might need to use parameters for Virtual Protect that have those bytes in them. So how are we going to get around that? Well, we can do some tricks like XORing registers with each other, or adding a large value, or subtracting a large value, or negating something. Being creative is kind of the name of the game with these exploits. But for the parameters that don't have bad bytes in them and our desired value, we're just going to put those directly into our payload, and then we'll use some placeholders for the rest of the parameters. So you can see there we have one parameter that has no null bytes in them, but we have 4 parameters that do have null bytes, so we'll just put in a placeholder there. One thing to note, we don't necessarily have to use the placeholder way. We could just push the values, but I think the placeholders make it easier to conceptualize. I think that's the easiest way to go when you're developing an exploit. Just an example of using that XOR to overcome those bad bytes, we're going to get one register to an arbitrary value that we know what it is, and then we're going to pop a value into our next register, and then once we XOR these 2 registers together, we can get our null byte value for our parameter in a ECX in this example, without actually ever supplying that in our payload, and that's really useful for us. So once we get our parameter set up in a register, we need to overwrite those placeholders that we put in. So 2 ways to do this are a push gadget was one, and that's a pretty common type of gadget. The push gadget shows up in JOP more commonly than the other type of gadget we'll talk about in a second. But with the push gadget, we're going to need to work with the stack pointer just because of how the push operation works. But we're only going to need to set 1 register aside for that. And with our move dword pointer gadget is the other way to do it. We don't have to worry about our stack pointer at all, but we're going to need to set 2 registers aside for that. Our first one will be our address to write, and then our second will be our value. With JOP, you need to worry about how many registers you're setting aside at one point, because you already have 2 always in use for getting your control flow to work, right? You need your dispatcher gadget address loaded, and you need your dispatch table loaded. So you need to consider that, because things get hard to work with when you don't have so many registers. But looking at an example of overriding a parameter with that push here, we're just going to need to relocate ESP once we get our value set up and our register. We're going to need to relocate ESP 4 bytes higher in memory than our placeholder. And so we'll add ESP 14 here to get ESP to the correct location. The push operation is going to overwrite ESP -4, so that top placeholder there, that top 7070 where the arrow is going to get overwritten once we execute our push. And then we will have gotten our first parameter set up. With move, we can do the same kind of thing. We just don't have to worry about ESP. So I'm skipping over all the XORing to get our register set up. We have EBX and ECX in this move dword pointer gadget. So our first register will be our address here on the stack, and then our second one, or in memory, not necessarily the stack, and then our second will be our value. So here, if we look right here, this placeholder is going to get overwritten with our value in ECX, and then we have our second one set up. So once we get all those parameters set up, we're ready to call our function, and we're just going to have to make sure ESP is in the right location so that our function uses the correct parameters. So that location that we want it to be at is just before all of those parameters in memory, and that'll just make sure that Virtual Protect uses the parameters we work so hard to set up. And then we'll find our pointer to Virtual Protect, and we're going to need to dereference it so we actually jump to their real address. So one way to do this is just to do a jump dword pointer gadget. Another way, we could also dereference it into a register and then jump straight to it. We could also dereference it in a register and then push that and then do a jump dword pointer ESP. And that seems a little complicated, but that's what we're going to do in our exploit. It works. So there's other ways to do this too. You just need to make sure that your jump goes the right level of indirection down, I guess would be the word. So we're going to take a quick look at a demo of this working. We're not going to spend too much time. We're just going to look at this playthrough and our debugger, this exploit, and see that our shellcode's going to run. So let me open that real quick. Here we go. We're going to start out with that JOP setup gadget that we're talking about. So we're going to get that EDX register set up and our EDI register set up. EDX is going to hold our dispatcher gadget address, as you can see in the top right. And then EDI, if you look in the bottom left, that's our dispatch table showing in our memory dump. We're in immunity here. Notice that we ended in that call like we were talking about. So we're doing things out of order a little bit here, but don't worry about that too much. See this pop EAX instruction happening in the top left, and that pop there is just to pop that value that got pushed with our call gadget like we were talking about. So that pop is just an extra one to handle that. And then we're going to get our first register set up, our first overwrite set up. We're going to end up with our shellcode's address in our ECX register, and then we're going to push that over our parameters. So we're adjusting ESP here to the right location so we can overwrite the right thing. If you see on our stack in the bottom right here, or in our dump in the bottom left in 1 second, we're going to overwrite that last parameter with our return address, which we want to go to our shellcode right away. So in a second, you'll see with this push, you can watch that down in the bottom left right now. Watch that last 7070 there. And when we push, we overwrite that with the address of our shellcode. And we've got 1 out of our 4 down. And then we'll just use that same value for our first parameter, so we don't even need to XOR again or do anything like that. We just need to move ESP and do another push on our first parameter. So our first placeholder there will get overwritten. Awesome. So we're going to skip over getting the register set up for the next 2 overwrites. We're going to use those move dword pointer gadgets though. So we're just going to go to our breakpoints in our debugger here and watch that happen. We're going to overwrite those last 2 placeholders that we need. So in a second, I'm watching the bottom left, the highlighted spot. We're going to overwrite that 1 time and then set up our registers again to overwrite the next one. And once we do that, we'll have our function call ready to go. So after we move ESP in the right spot, we're going to dereference the virtual protect pointer. We have that pointer in ECX right now. Then we're going to dereference it into the register. And then we're going to push that register like we were talking about, a little complicated way of doing this. But we're going to push it, and then we're going to do a jump dword pointer ESP in 1 second. Awesome. So immunity will show us that we have our parameters set up well. We have our address right, our size right, and once we execute virtual protect, we'll return to our awesome shellcode, which will spawn a message box saying, hey guys, we finally did it. We finally got done with this exploit. And yeah, so now with that demo done, I'm going to pass it back on to Bramwell to talk more about the JOP rocket and explain how with the JOP rocket we might be able to get around some of this difficult process of developing our exploit.
Now let's talk honestly here. Some hard realities with JOP. It's a great technique. It's a wonderful technique, and it can work well under ideal circumstances. Guess what? Circumstances will not always be ideal. The most important thing that we need is our dispatcher gadget. No dispatcher gadget, sorry, too bad, good luck. But the JOP rocket is determined to find every form of the dispatcher gadget, the good ones, the bad ones. It'll find them all. And some work better than others. So that is a consideration. We got to have a dispatcher gadget. The dispatcher gadget, again, is what directs the control flow. With ROP, we do that with the stack. With JOP, we use the dispatcher gadget and the dispatch table. So if you're missing that, then nothing else really matters. And there's also the issue of there's just not a lot of JOP gadgets compared to ROP. Sad but true. But sometimes there's enough. And then honestly, if you're able to do ROP, it's going to probably be easier a lot of times and maybe less trouble. But it's always worth taking a look to see if there are the appropriate gadgets for JOP. If there are, good, try it. It may be worth the effort. So recently, another thing that I did is, with respect to addressing the dispatcher gadget, again, most important, got to have the dispatcher gadget is, when we look initially with ROP, you look for the return, you look for the opcode C3 and a couple other variants, but primarily C3. With JOP, there are many other opcodes that you look for. So for the jump D-word pointer, we do FF20, FF23, etc. And that's just a few. There are a couple, other variations. So recently I came upon the idea of what if we did jump D-word pointer EAX plus or minus an offset? It's still perfectly valid for dispatcher gadget. It still works. It still does what it needs to do. But look, the opcodes there are entirely different. So we've incorporated this very recently into the JOP rocket just to provide additional assurances that every form, every gadget, every dispatcher gadget is found. So make sure that we get the gadgets that we need. Now, as I was working on JOP Rocket version 2.0 over the summer and the fall, I wanted to really simplify it because honestly, a lot of the stuff that so far it seems kind of complex. And if you watch our DEF CON presentation, the code that we had, very complex. It's definitely not friendly to a novice. So let's explore why you may want to do the more difficult version of JOP, because it certainly can be kind of ugly and some interesting code reuse trickery going on. Maybe you want to prove that you're elite, that you're a JOP whisperer. Maybe you want to empower yourself by taking up the mantle of the so-called the black art of JOP, which some had claimed had never before been done in the wild. Not true, but very, very seldom. So if you could do that, then wow, you're doing something very, very unique. And maybe there's a more practical reason. Maybe you just simply want to bypass ROP heuristics. So given that, would we dare to simplify this JOP? Do we have the nerve? Well, might as well. Let's do it. Let's see what happens. And so, JOP doesn't always have to be hard. It's great when it is, but if we can simplify it, then it's going to make it more accessible. Now, last year, teaching very hardcore, challenging ROP to students, as well as JOP, I was confronted by an interesting observation. One said that he thought that JOP was easier than ROP, but that was under ideal circumstances. So what are these ideal circumstances? Well, let's explore that. Now with ROP, where the ideal is, this is exact same technique that the Mona uses. It tries to populate all the registers with the parameters for the Windows API. And then you do a push add. What push add does is it pushes everything onto the stack in a predefined order. And thus you can get your call set up and you make the call, and then you can bypass dep, which is going to be one of the primary goals of code reuse attacks. With JOP, it's actually much, much easier. Don't have to mess with setting up registers for parameters. Instead, you could just preload all the arguments and directly dump them onto the stack. Then you just get your virtual protect or alloc pointer, dereference it, and then make a jump. And literally that simple. So a lot less moving pieces than ROP. Again, ideal circumstances. Now, before we get a little bit further, let's talk a little bit about this idea of pre-built chains. So pre-built ROP chains, something created and only provided by Mona from the Corland team. It builds you out a chain, gives you a good starting point, so you don't have to go and create the exploit or the ROP yourself. It's already provided for you. Sometimes it works very well with just a minimal tweaking. Other times you got to do a lot of work. Sometimes it is useless, and you got to do everything by hand. But at the very least, it gives you a really good starting point. It provides kind of a base skeleton to work from. And so my idea was, well, could we take that same concept and apply it to the JOP rocket, apply it to JOP? And at first I thought, no, that's outrageous. You can't do that. And the reason why was because with ROP, it's a lot simpler. We just have the C3, the return that allows us to kind of order our control flow. With JOP, there are many other possibilities. You jump EAX, jump EBX, ECX, etc., and calls, and there's a lot of different moving pieces. How could we package that together in something that we can automate? So it seemed too challenging, too many different possibilities. If you do the math on it, there's a lot of possibilities. But I decided to heck with it. Let's do it. And so this September 2020, to commemorate Wild West Hackin Fest, we are releasing for the first time ever the ability to generate pre-built JOP chains. How cool is that? And so how this works is the JOP rocket tries to set up chains for each indirect branch. So jump EAX, EBX, ECX, etc. And it just populates it with all the necessary gadgets. It does 5 for each register. So a total of up to 35 for VirtualAlloc, for Virtual Protect, different variations, provided that there are enough for distinct chains. If there's only 1 or 2, then of course it's not going to generate 5. But at the very least, that's what it tries to do. So specifically what it does is it tries to discover the dispatcher gadget. It takes note of the padding. It does that for you. It gets you set up with ROP. So we use 2 ROP gadgets to start the JOP, and then we discover the pointer to VirtualAlloc, Virtual Protect, and then it works on a series of doing stack pivots. So stack pivots, a combination of multiple stack pivots, and then we can reach our parameters. And then we jump to it. So quick and dirty method with JOP Rocket, 2 steps, 1, 2. First step is we do the S, and we just get everything. We get all of our gadgets. We get the necessary ROP gadgets too. And then G to generate, and it builds the chain. Now, if you know exactly what you want to do, say that you're going to do a stack pivot of, say, 1,000 instead of the default of 75, then you can specify that. So it makes it more accurate. If you want more pre-built chains or less, you can do that. If there are 25 distinct chains that it could produce, 25 entirely different ones, you could specify that. Or maybe you only want 2 or 3 of each. Totally up to you. Now, before you try to do this technique, it's a good idea to think whether the stack pivot technique would actually work for this particular binary. It may not be feasible, but it also bears repeating that, even if you're doing stuff on the heap instead of the stack, you can redirect ESP to point to the heap. So there are many possibilities. So let's look here at the results of the JOP rocket. Literally, this is what the JOP rocket created. Created a nice, beautiful Python script. We have one for VirtualAlloc, and it pre-populates it. So this is the exact same wave read that we did at DEF CON a year ago. It had a very complex script. Virtual Protect, we got the pointer for Virtual Protect there, and it does everything. Believe it or not, this actually more or less works. Now, there's one other tweak you got to make over here, and you also have to take into consideration some of the practicalities of dealing with a wave So it has to be a valid WAV file. But let's look specifically at how this works. So get into it here. So we're going to start things off with ROP. We're going to load EDX with a dispatcher gadget, and then we're going to load EDI with our dispatch table. So we need those two things. And now that we can start our job, we jump to EDX and we're done with ROP. Now, of course, for these steps, you can also do it in JOP if you want to. So what we're doing now is we're doing a stack pivot of 894. We're doing it once again. And then we are going to load EAX with a pointer to virtual protect, and then we're going to make a jump to the dereference virtual protect. And now we can bundle up our JOP gadgets. And here are the stack parameters, the arguments for virtual protect. You'll want to personalize these for whatever binary that you're dealing with. And then we take everything, we package it together. It's in the form of a payload, and it's ready to go. Under ideal circumstances, this would work with just minimal tweaking. And again, this is the exact same binary we did at DEF CON, and more or less, with a little tweaking, it works. So let's take a look at it, see it in action, a brief clip here. So we're going to do a stack pivot of 894, and then we're going to add 10 to our dispatcher gadget. We got that there. We're going to stack pivot once again, back into the dispatcher gadget. And now we're popping into EX, loading the pointer to virtual protect, and then we're going to make a jump dereference call to that dispatcher gadget. So now we're about to make the call. Everything is on the stack. It is ready to go. And we're going to do the jump, and it should work. We should get our shellcode, and will it? Oh, my goodness. We did it. Yes. That Rocket Cat got her shellcode. Sweet victory. So it can work with a little bit minimal effort, but it bears repeating once again that you got to be able to tweak the JOP. So it just gives you a starting point. So sometimes it's just a little bit tweaking. Ideal requirements here is no bad characters. Under those circumstances, sometimes it could work with very little effort. Some functions inherently don't have bad character restrictions. Others do. If you do have bad character restrictions, that's okay. We can still deal with it. So let's look at one way to deal with that here is we have, say we want to get the CD, that's a bad byte for whatever reason. And we decide instead to do the unassemble with a JOP rocket. We plug in the 13CE and oh, lo and behold, add EDI. I'll do that because below that I have push EBP. I avoid the CD bad byte because I'm using CA instead. That's one way to do it. Another way is to do our exclusive OR. So doing exclusive OR can be a lifesaver. Exclusive OR, negate, those types of things. So say we want 00406020, got that bad byte, got the no byte, the 00. How can we avoid that? Well, with exclusive OR XOR, we can take any three values and we can go back and forth. So we can have an encrypted form, and then we can have the XOR key, and then we can transform it. So we'll just plug in the encrypted form, do our XOR magic, and boom, we got it. So the dummy variables that Austin described, they're useful. So use them. If you have bad bytes to worry about, then use these placeholders. You'll use you can do AA, BB, CC, and then you can overwrite these placeholders. The best way to do that with JOP is by using push. It's a technique that you can't really use with ROP, so it is very much unique to JOP. So pushing is the best way to do it. And it's much more plentiful than the move dereference. But move dereference is another good way. So let's take a look at that. So we can load the encrypted form. We can do our XOR key. We can do the transformation. And then we just increment to the next placeholder. So it's a cycle. We can cycle through all the different variables and replace them, however many. We can reuse the same few gadgets, so you only need a few of them. That's simple. And JOP Rocket delivers for us, so jump with joy because it'll find everything you need. So if you want the move dereference, it'll find it. There you go, got it. We got our pops, we got our pushes, everything. It finds it for you. Some final thoughts here on ASLR. Now, ASLR, depth, those have been thorns in our side for a while. But just like with ROP, we can overcome them with, well, not too much difficulty. And the same is true with JOP. We can easily address virtual protect or easily address depth by using Virtual Protect, VirtualAlloc, etc. And we've always done that with every JOP exploit we've done. So there's no restriction there. ASLR, you can bypass that. We've done it. We've done bypasses of ASLR depth by using JOP. You just want to take into consideration, say, a memory disclosure, tweak it a bit. Maybe you get a pointer to a function, extrapolate from that. There you go, bypass of ASLR. Glossing over it, obviously. So JOP is Turing complete. Anything with ROP you can potentially do with JOP, arbitrary computation, provided that there's enough gadgets. If you're doing a tiny little gadget, then there may not be enough. So I want to invite you to try it for yourself. Go to joprocket.com. You can go to our GitHub. And we created 2 very special binaries that are intentionally vulnerable, and JOP will work on them. So there's an easier and there's a harder. There's one with no bytes and one with no bytes. So try it out. See if you can do the job. Final takeaways is be inspired. You made it through this talk. This is not an easy talk. There's a lot of technical, low-level detail that a lot of people don't deal with on a daily basis. So just getting through this and listening and understanding, even half of it, I think, is a good accomplishment. Be empowered. Don't be afraid to embrace the mantle of low-level software exploitation. Do your own ROP. Do your own JOP. It's something that each and every one of us is capable of doing. You can feel so much exhilaration when you're able to get an exploit to work. So liberate yourself. Don't be dependent upon others. Create your own exploit, your own 0 days. And if you're doing it, you like the ROP, try JOP for an extra challenge. And so with that, we would like to thank you for your time and thank you for honoring our mission or our commitment to honor Rocket Cats everywhere.
That
Already?
was
Oh,
incredible.
already.
Thank you. I'm
Thanks.
thinking, how many Rocket Cats were harmed in the making of your presentation?
There were a
It-
few, but
It was all a
most of
long
them
time
didn't
ago.
survive because, it is
They're
kind of
very
a
old
one-way
paintings.
street.
We have a CS student who showed up in here and he's been watching with like gigantic dinner plate size eyes, like, oh my gosh, I have to go watch this again because he only caught the tail end of it.
There is a lot to
notice,
take
but there
in.
there was also some rocket birds in there in some of the slides. I just realized that just now. So
Yeah, these are actual ancient manuscripts from 1400s. Not historically accurate, but